Normally, we type shell commands one at a time directly into the shell program in response to a prompt. But if we put a sequence of shell commands into a file, just an ordinary text file, then we can get the shell to execute those commands by just giving the name of the file. We usually call such files shell scripts. Let me show you an example. I have a file called my commands that contains some shell commands, like this. I can run it using the command /bin/bash, that's the name of my shell, space my commands. So that tells the shell, the bash shell, to take that file and run each command in turn. Now, in that case, I had to put the name of the shell program that I wanted to use to interpret my commands in the file. But we can run shell scripts without explicitly invoking the shell by putting the line #!bin/bash, if I'm using bash, at the beginning of the file. This is the first line in the file. Now, this line specifies the program that will be used to interpret the lines in the rest of the file. So in our case, we're using bash, and it's stored in the directory /bin. We can usually use other command interpreters. Let's say you wanted to use a different shell, such as say C shell or Z shell or one of the many other shells, K shell. You simply put the file path name of the shell program just after the #! on the first line. You can even write your own command interpreter and use that. Invent your own shell. The reason for the #! characters is that when you use the exec system call to get the system to start a new program, right, we give it a file name and the kernel usually will load that file into memory and start it running. Well, what happens is the kernel first checks that the file has the execute permission set, and you can do that by using the chmod command to set the execute permission. But then it looks at the first few bytes of the file to find out what type of executable file it is. And in the early days of Unix, this was a 2-byte or 16-bit number that they called the magic number of the file. This was the thing that specified what type of file it was. And they made the binary representation of the two characters, #! Using the ASCII character code, they made that binary representation the magic number for a script file. Now this happens to be the hexadecimal number 2313, and that's the ASCII character code for the #23 and the ! 13. So they made this the magic number for to specify a script that'll be interpreted by another program. Shell scripts are incredibly useful. They are essentially programs. Since the shell has variables, we know that, and it has control structures like if, for, while, case, just like any other programming language. In addition, the shell has can use a number of very powerful commands for processing text. These are programs that just come with the Unix system. And they can be combined in pipelines and placed in shell scripts, and you can choose between them using if statements and so on to build a program in a sort of a shell language. You've got commands like cut to remove parts of a line, WC that's word count to count lines, words and characters, TR translates characters from one set to another, grep is used to search for lines that match a pattern, sort to sort lines, and so on. We can automate a lot of simple text processing using a set of shell commands, often in a shell pipeline. Whenever you have a task that involves a set of shell commands, a shell script is a good option. A very common example of this is the processing of system log files. Many system processes keep a log of their actions. So for example, a web server might write a log entry, that is a line of text, into a file whenever a request arrives for a web page. And that log entry might include all sorts of details about who's making the request, in other words the internet address, what page it's asking for, what time this occurred, how much data was transferred, and so on. These logs can be processed and useful information extracted using a shell script and the text processing commands that I mentioned. You might want to count how many web accesses came from a particular network address, or how many times a particular web page was accessed. This is easy to do using a simple shell script. Just to give you a fun example, here's my favorite short example of the power of a shell script. It's a complete spell checker written in a single shell pipeline. Now, these days we have spell checkers built into word processors and we don't need it, but it just shows you the power of this approach, and we can do it in just a few minutes. Now the pipeline is quite long, so it makes sense to put it in a file and make it a script. And so here it is. Now you know that the first line is the line that will specify the shell program to use, bin bash in this case. Now I've broken it down here into separate lines to make it a bit easier. The first line here will translate all the characters that are not in the set capital A to Z, little a to Z. Anything that's not in that set will be converted into a new line. And in addition, if we have multiple characters that are translated to the new line, they're squeezed down to a single new line. So that's what that first command does. And it's using $1, which is the first argument for the shell script. So that's the file we're going to be doing the spell checking on. The next line translates all the uppercase alphabetics, A to Z, to lowercase alphabetics. The following line, the sort -u, is going to sort the whole file into alphabetical order, and the -u means remove any duplicates. It stands for unique. If it finds multiple copies of the one word, just put one, leave one in there. The last command here, this com -23 -userdict words, now this one, what it does is it compares the two files. In other words, the file of words that you've now extracted from your document and a file of words from a dictionary. And they're both sorted, so it will only print out the words that are in your file but are not in the dictionary. And these words are likely to be misspelled words. Now, when your shell, in this case bash, starts up, either when you log in or when you are about to interpret a script, the shell executes some commands that are found in a few standard files, a few sort of standard shell scripts. At login, bash first reads commands from /etc/profile, and then from the ~/.bash_profile file. Now, this tilde, this refers to the user's home directory. This is translated by the shell into the home directory of the user. And the leading dot there on the file means they're hidden files, so a normal ls won't display them. You can tell ls that you want them displayed, but normally they wouldn't be displayed. It also reads commands from the ~/.bash login and the ~/.profile in that order. In addition, when starting up any shell script, the file ~/.bashrc is read first. Now, the reason for all this is that it allows you to set up standard configurations for shell scripts. So when you're running a shell script, it will read these files and it might set up environment variables. That's the most common use. It will initialize some environment variables that are then passed into any programs you're using. Now, anyone can write a shell program. There's nothing stopping you from writing your own shell program and setting it up so that your scripts will be run using that program. It's just a program that reads from standard input, interprets lines of text, and does some action. Now, any normal shell would break the input line into parameters and then use fork exec to start the relevant program. And your shell would also interpret the $ variables and redirection of input and output with the greater than and the less than and so on before starting up the program. This means that as well as shell scripts, in other words, files of shell commands, languages that are not compiled, such as Python, can be run in this way. And this is the standard way of running a Python program. So at the beginning of your Python program, you put a line that says #/userbin/python. That's assuming your Python interpreter is stored in the directory userbin. So here's an example of a trivial program to print out hello world, and you can see the first line there specifies the Python program to run to interpret the rest of the script, which is my Python program. Now, if the Python program you're trying to run is executable, in other words, has the execute permission bit set, and it's on your search path, then you can run it like any other command. Now, when a shell runs a program, it looks for the file containing the program in a set of directories that are specified in the shell variable $path. If we set the path variable like this, path equals /bin:/userbin:, then the shell will first look in the /bin directory for the program, then in the userbin directory, and then it'll give an error message if it can't find the program. Now, if we give a full path name for a program, then it doesn't actually use the $path variable because it knows exactly where you think the program is. So /home/bob/myprog means look in the directory /home/bob for the program myprog. If a program you want to run is in the current directory, then you can run it with ./myprog. That's explicitly naming the current directory. If we put into the path variable the current directory or dot like this, path equals $path:, then the shell will automatically look in the current directory and you can run your program by simply typing its name, myprog. Of course, the file there has to be executable as well. Now, all those startup scripts that I described are the place to set any shell variables you want available in your programs. So this is where you set your path variable, for example. And you can edit that, this .profile in your home directory. You can edit that and put a path setting statement in there. You can set your path to all the usual places, but you could also, for example, create your own directory, let's say mybin, and put mybin ~/mybin into your path variable like this, path equals $path:, ~/mybin. Now in this video I've introduced the idea of a shell script, in other words a file containing a whole lot of shell commands, the idea of the #! And path name for an interpreter for the file, which lets us invoke shell scripts easily or run other interpreted languages like Python. I've talked about the path variable, and I've talked about shell scripts that are run at startup.